Hello everyone and welcome back to a new video in our Etabs video series in which we are going to basically model us a very simplified beam. The reason why we are modeling simplified stuff for now is because we want to establish some basic principles before we dive into the world of modeling structures using Etabs. So of course this video series is only going to get more advanced as time goes. With that being said, sit back, relax and enjoy the show. Okay, so first things first, I'm going to click on New Model. When I click on New Model, I am greeted with this little model initialization template, in which I'm going to ask him to use the built-in settings, and I'm going to opt for metric units. I'll click OK, and I'm greeted with yet another window that tells me basically a quick model template if I want to define a quick model template. I don't want to define anything, so I'll click here on blank. And still, even if I apply blank, you can see that there are some grid dimensions that are being pre-initialized for us, as well as some story dimensions are being pre-initialized for us. I just ignore it and click OK because I'm not doing any multi-story stuff. But just keep those numbers in mind. He's going to define me for stories with heights, and he's going to define me some grids with spacings. So I click OK, knowing that this will be defined. Of course, Etabs takes a little bit of time while it's preparing the GUI and graphical user systems. And you can see him providing me with this 3D view with a grid that we have defined. And also, if you take a look, this is the 3D view. And if you take a look here, this is the plan view, or basically the top-down view. And you can see you are standing at story 4 at z equals 12. Now, why are we at story 4 at z equals 12? Because when we just defined our structure on this side, if you remember, he is going to define us for stories with heights of 3 meters. You can go up and down the stories by basically clicking on those buttons. If you go up, it will cycle back to 0 because 12 was the last one. Go up again, it goes up to 3, to 6, to 9. Also, if you cycle down, it goes back to 6, 3, and 0. Of course, if I forget what the stories are, I can click on Structures Layout, take a look on stories, and you see those stories defined with all their glory. Okay, now, what would I do to define a very simplified beam? Now, if you want to dive head first, which is not correct, to be honest, you would go to Draw and just click Draw Beam and click Quick Draw Beam or something, or just Draw. If you try to draw something very quickly, you will end up being very frustrated because it seems it's not clicking anywhere, as you can see. There is nothing to be clicked, nothing is being added. You still don't get anything because you have not defined anything to basically align to. What you see here is a grid, yes, but Etabs needs you to define a structural axis grid, and this is not enough. I don't want to give too much information in our first video, so allow me to explain. I will hit escape button to get out of the command, and just remind you that we need structural axis, not this basic grid. We need structural axis for Etabs to understand how to draw the beam. There is a lot of more details, but this is our second video, so I will try to keep it as simple as possible. So, okay, he wants a structural axis grid. He gets a structural axis grid. I click on grid here, so model, structure layout, grid. You see G1 is defined. Double click on it, and it opens for you the grid editor. This is basically like the structural axis in Autodesk Robot. You have nothing in X as grids, you have nothing in Y as grids, and there is no Z grid. Why is there no Z grid? There is no Z grid because the Z grid is being defined by the stories that we can define here. So those grids is basically the XY components of your axis. I want him to, of course, you could do some origins here and change the origin and so on. This is some advanced stuff that you might use. For now, I will not use that. I will just simply say, add me a grid. And let's say we want to make a 2-span beam. The first span is 5 meters, and the second span is 3 meters. So I need 3 points in the X to make the span. I say point number 1, which starts at 0. I'll add another point number 2, which has the X coordinate of 5. And point number 3, which has the X coordinate of 8. With those coordinates, I would have a 2-span beam. The first span is between 0 and 5, which is 5 meters. And the second span is between 5 and 8, which is basically 3 meters. This bubble location means the location of this bubble of the axis. You can change the location of the axis, but I will keep it at the end. Now we need still to add some Y grid, so I click here. I will not have any Y grids because I'm doing only a beam. I would need this if I have a structure, so I just say this is grid number 1 and that's my Y grid. Since we finished, I can just hit the OK button here, and you will see that the grid just got imported here. Now with those grids being set, of course, the software is not really understanding what you're doing because it's not used to having a simple beam. It's used to having structures. So let's ignore what we see here for now. And let's focus on our 2D grid here. I want to draw some stuff. So if I want to draw a beam, I need to define the material of the beam, I need to define the section of the beam, and I need to define the forces on the beam. So I click on define and define materials. You see, now I have multiple materials, most of them are steel, and I can see a concrete material of 4000 psi, which is around 28 megapascals. I could use it, or I could add a new material, and I can use any region I want. For example, I could even add a European material, which is okay for now because I'm not designing anything. I want, for example, concrete, and I want to use a concrete of 30 over 37 megapascal. Of course, the standard here is the Eurocode 1992, the one for the material. If I click OK, you see, of course, it gives me some more options to define because now it imported the options of the concrete from the Eurocode and still allows you to change some stuff if you want to change anything from those things. I think I'll accept that, so I'll just click OK, and that's that. If I kind of want to check out or change anything here, I can double click again and it opens me the material definition. Or I can just click on modify show material and it opens me the same edit window. If you click delete material, it will delete the material. If you add a copy of a material, well, it will add another copy of the material, and you can change the name of the material as matte, for example. Click OK, and you get another material copy of the original material, which I will delete right now because I don't need it. Okay, so I defined the material. I still need to define the cross section. There is a lot of things that we define later, but for now, let's keep it simple. I'm going to define me a cross section. It's going to be a frame section. Yes, the bar elements are called frame elements in Etabs, meaning that the section of the column is a frame section, the section of a beam is a frame section, and even the section of a bracing is still a frame section. I click on this, and of course I have some predefined sections I will not be using. I will add me a new property. Now adding a new property means basically that I'm going to add a new section. Import means I'm going to import from the outside. Add a copy means I'm going to copy it. Show means I double click and modify whatever is inside. Delete multiple properties will delete multiple things. You can see the idea. I might be explaining those things in the future when need be. I'll add a new property. Of course, it gives me frequently used shapes. And of course, I can go full parametric to give the AX and AY and AZ, IX, IY, or if you want to have some composite sections. I'm going to go to my concrete section rectangular, and I'm going to define the concrete section to be depth. You know what? I will accept whatever this is. Depth is 900, width is 600. It's kind of a big beam, but I will keep it. See the section name, I think FSEC is not really that good, so I will call it beam concrete 600 by 900. B by W, W by H. Display color, I can change it if I want. I will keep it. And there are notes if you want to add notes to your section, like give something internally. The material of the section is going to be C3037. And something very important I want to talk about is those 2 and 3. What is this 2 and 3? Now, first of all, this stuff, those points are the reinforcement bar location points. You could show them and hide them and change them, but this is something that we will be talking about when we reach the later stages of Etabs, when we start designing our cross sections. For now, we just want to know that those things exist. Property modifiers are basically things that change for you the inertias. For example, if you want to model a frame and abide by the ASIA code, you might need to change the inertia of the columns to become 0.7 and the inertia of beams to become 0.35, something that I will leave for later. For now, I'll just do a simple beam. What is very important to note is this 2 and 3 arrow. And to explain that, I need paint. So I'll quickly, and that's why I told you I'm going to do a simple beam, because there is so much to unpack. Let's say we have a beam. In 3D, it kind of looks like this. Of course, the beam is going to be under loads that will cause shear and bending and whatnot. Now, let's say the beam is also under other loads, which are basically wind loads. Those are out of plane loads. Also, the beam could have axial loads, which are, well, as the name suggests, axial, so I could have loads like this. Those are the possible loadings of the beam. Now, from those loadings that are applied on the beam, you will have moments and shear and whatnot. So allow me to draw you another beam where I want to discuss the shear and moment and stuff that you would get on the beam. On the beam, you have 3 moments and you have 3 forces as internal forces. You have an internal force in the axial you have an internal force in the axial direction, and of course, that's called an axial load or axial force. This axis is called axis number 1. The local x-axis in Etabs is called axis number 1. Of course, you could have moment around, so this is basically, so the force in 1 is your axial force. What about the moment around 1? The moment around 1 is going to be your torque. So moment around 1 is going to be your torque or torsion. That's axis number 1. Axis number 2 in Etabs goes up, local up. This might correspond to the local z-axis if you want to call it z. And this has, of course, 2 things. You could have forces on that axis, and you could have moments on that axis. A force on that axis, I will call it F2 now, is basically your in-plane shear. The shear force that is resulting from, of course, you need to talk about the directions later, but the internal shear force resulting from the gravity loads, basically, the in-plane loads, which are the red loads here. The moment around this thing, if you have a moment around this axis, it's called M2 in Etabs, or some people call it M2 too. And that's basically the out-of-plane bending. And this out-of-plane bending, I will put a circle with this color around it. This out-of-plane bending is a result of having those loads because they push and bend the beam out of plane. M33, so the axis number 3, and I will draw it in green, goes in this way. And that might be your local y if you want to call it y. Now this here is your axis number 3. The force in the direction of axis number 3, F3, is going to be your out-of-plane shear. This is, of course, caused by the magenta force, or whatever that color is. I'm not really good in colors. This is caused, F3 is caused by those forces, like wind loads. Then you have moment around that axis. The moment around the axis, this moment is called M3, and it's your regular bending moment that is resulting from in-plane forces, which means forces that are from gravity loads. I'll put a red circle around this just to denote that the ones that cause M3 are basically those forces. I hope that makes sense because I will keep referring to this video when I talk about the local axis directions of Etabs. So I hope this puts the issue of local axis to bed. I click OK, so I defined me a section now, OK. And now let's draw us a beam. There is a lot of things to unpack in Etabs, but I will talk about this later. I click on draw beam or column or brace object. I click on this, and now I can draw. You can see my arrow changing. Before I draw, take a look at this. Property steel column. No, I don't want a steel column. I want my 600 by 900 section. Now I could mess it up. Like for example, let me show you what happens if I just click on steel beam. For example, let me just draw something like this. Of course, I clicked here, and now I'm dragging my beam, as you can see. And I click here, and it continues dragging the beam. Notice I'm drawing using steel beam. That's incorrect. I click here, and this ends my drawing procedure. I click escape, and now I would see it here, and I should be seeing it also in the 3D. Yeah, there we go. In the 3D element that you can see here. Now, I have messed up my section because I called it steel section. If you want to check it out, you can right-click on the element and see its properties. And if you right-click on the element and see its properties, you can see that the section is steel beam. You can change the section from here if you want. That's okay. And there are other things you can talk about here, but I will talk about those later. Another way of changing the section is to go to assign, and you can assign to a frame a section. In this case, you can select the section and assign it to those things and click the apply or OK button. I click apply and OK. And now the sections are assigned, as you can see from the name here, the label. You can also right-click and see the section being correctly assigned. Notice that Etabs seems to show you the last thing that you have used, so it makes sense. What else remains is, well, we need to add some loads. Also, we need to add some supports. Notice Etabs drew for you some sort of support automatically because you have drawn the beam on the ground. There is some strange thing that happens to Etabs sometimes. If you followed this tutorial so far and didn't find any supports here, then make sure that you are drawing on z equals 0. And if you're not drawing on z equals 0, you can go up and down using this move up, move down until you are at z equals 0. Or regardless, you can just assign a support because we're going to change those supports. Also, something else I want to mention is if you draw while having the one story active, then whatever you draw affects only this story. If you click here and say all stories, then when you draw a beam, it will draw not only a beam on the base level at the moment, it will draw the beam on the base level, on the first level, on the second level, and so on. This all story helps a lot when you want to draw a multi-story building that has similar stories. There is even a command called similar stories. We'll be talking about those later. I think we're doing good so far. Now I need to add some supports. So I click on assign, and there is something called joint assign, because the support is part of joint. And there's something called restraint. Restraint is the name of support in Etabs. If you click on that, you can see the typical support definition, in which you have to, a support is basically something that stops the structure from moving. Now, at the moment, you have pins here, and this will cause an unstable structure in 3D, because the structure will be allowed to rotate around its local axis X, which will cause a shaft. I'm going to make the rotation around X and the rotation around Z impossible, just for the, or you know what, I'm going to make me a fixed support and basically apply this fixed support here. So I select, you see what I did? I selected the node and hit the apply button and then the OK button. And it seems it did not refresh here. Let me check very quickly. It seems it did not refresh. So how do I check? Well, I stand on the grid, right click, and check. Restraint is UX, UI, UZ, RX, RY, RZ, exactly as I want. And just use another software to see something here, but it seems that this little star is just a symbol that is used for all types of restraint. Maybe I'm wrong, maybe it needs time to refresh, but I will accept that. The last thing that I need to do for my example today is to add some forces. Now, to add some forces, I need to make sure that the load case is correctly selected, but I haven't defined any load cases so far. Now, the structure comes predefined with dead and live load cases. If you go to loads and check out the load patterns, you can see dead and live. And if you go to load cases, you can see dead and live, and even modal. So the load cases are already predefined for you. I will not define load cases today because, once again, I try to keep my first video as simple as possible and to the point. This is just a break the ice video, an introductory video in Etabs. My Etabs YouTube tutorial is going to follow a similar steps to my Autodesk robot tutorial. So check out that one if you want to get more ideas about my plan for this series. It's going to start small, so let's continue with it. I'll go to assign, go to frame loads, because that's how you define frame loads. And you can define some stuff here. I don't want to define nodal loads. I want to define bar loads. So I click on distributed, opens this. Asks you what the type of the load is. It's dead. It asks you what the direction of the load is. It's gravity, so down. You could basically change the direction. You could, for example, apply a force that is in the local 2 of the element, local 3 of the element, global X, global Y. Gravity is -Z. Of course, you could have projected forces. I'll keep it to gravity because it goes down. Now I can define a trapezoidal load made out of 4 points. Now my load that I'm trying to define today is not a trapezoidal load. I'm going to try to define me a uniform load. The uniform load's value is going to be 10 kilonewton per meter. I could put 10 here everywhere, like 10, 10, so on. Notice that the distances are relative. Can make them in meters. Or I can just go to here and say 10, which is an abstract version of this entire thing. Of course, I need to select my elements, so let me just... And by the way, those tricks in zooming in and out, those are by the mouse. If you hit the mouse wheel in forward, you can zoom in. Mouse wheel back, you can zoom out. If you click the mouse wheel, you can pan, which is kind of cool. I select those elements, click apply, and now I can see forces. 20s or 10s. Oh, okay. You see 20s here because I messed up. You see, I defined 10s here and defined the 10 here, so they added them up. So you see, it applies this definition plus this definition. I can remove that thing by either basically applying another force, because you can see here the option saying replace existing nodes. So when you apply something, it will delete the old one and apply the new one. Or I can basically just delete. Oh, I need to select them. I can basically delete like this and apply another load. This time I will not make a mistake. So I'll make them all zeros because I only want to have a uniform load. Once again, selecting this, I'll apply. Now I have 10s. If I say OK, well, OK, fine, I see 10s, but I want to see the distributed arrows, right? How can I do that? Notice that you have two windows. You can show something in window 1 and something else in window 2, which is kind of cool. If you click on here, which is called display, well, by the way, those are your display settings. If you select display shall load assigns, you can ask him, if you click on display frame load assigns, you can ask him to show you the loads on the frame. Of course, you can ask for a certain load pattern. I want dead, so let's apply that. And I can see the load in its glory. That's not enough for me because I want to see it in 3D. So if you click here and hit apply, you can see it in 3D. Of course, in 3D, it kind of looks cooler because you have the arrows. So if you come closer, you can see the arrows there denoting to you, of course, this is 3D, that you have done it. You can also orbit, and you can see those arrows in their 3D glory. It's up to you what you want to see. You want to see them as arrows, you want to see it as just a label. It's up to you. Fine with me. Notice you don't see any arrows here because you're looking from top down, so those arrows are not invisible for you here. Oh, look, the label changed here as fixed, so it was just a refreshing issue because I was expecting it to change. Okay, I think we are almost done, so I can run the analysis now. How do I run the analysis? Well, you can go to Analyze, Run Analysis. There are other things like Check Model and so on. You can hit the F5 button or click here, or you can click the Play button here. All of them will run the analysis. Now, Etabs will immediately ask you to save the structure because it will produce you a lot of files. I'll save it in a structure called R. You can just say, for example, here, tutorial, and hit save. And now it will start analyzing. Because now I don't have any control. My mouse is not moving. It's running. I don't have any control on anything on the GUI. You can see my mouse just floating around. There are some warning messages. For example, here, when it tries to run a modal analysis, of course, I don't care about anything about the modal analysis because I don't want it to run a modal analysis. It's telling you that there is no restraint masses because in modal analysis, you have to have masses. I don't care about that because I don't want the modal analysis anyway. I close this, check, it immediately draws you the deflection shape, which is kind of cool. I want to see the moment diagram and shear force diagram and so on. So basically, I'll go to this little thing, or F8. If you hit F8 or click this button, it will display to you the diagrams. Notice that my active window is this one. So whatever I change here is going to affect this one. I'm selecting the load case dead because I defined my loads in the dead case. Let's take a look. You see, axial force, shear 2.2, shear 3.3, torsion, moment 2.2, moment 3.3, those things I explained here. I want moment 3.3, which is my bending moment diagram. If I click apply, you will see it. Of course, you can change a little bit. For example, I want to see the values. That's easy. You have to click on show values at controlling stations. If you hit apply, you will see the values at the controlling stations, which are, there we go. And by the way, it did not refresh, so I had to jerk it around. Those values are given on the maximum points. If you move your cursor on the element, you can see the values switching and moving. Notice how Etabs is approximating things. If you know the finite element method, and I have a video series running, and I'll link it top right, you know that this should be a parabola, but it's not. You see, Etabs in its analysis breaks the beams into little small beamlets, or finite elements, and calculates the internal moment at those ends, without any diagrams in between. If you want to reverse engineer Etabs, it's very easy. Take a look. This is 5 meters. How many pieces have you divided? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it seems Etabs divides the elements into 0.5 meter pieces. If you look at the 3 meters, you can expect that it should be 6 pieces, and 1, 2, 3, 4, 5, 6. Indeed it is. If you want to see the shear force diagram, you have to talk shear 2.2. I think it's better that I click here on the 3D view and ask it to show me the shear 2.2 because I want to see two things. So I see now on the right side the shear diagram, on the left side the moment diagram. Oddly, it draws the positive moment upwards, which is kind of okay, I guess, but usually I'm used to seeing positive down. It's just a difference of opinion. If you want to go into the detailed stuff, you can right-click on any element and it will show you some details about the element. If I right-click, for example, at this element, it shows you the details of that element. You can see that it's showing you now for the dead load case. You can see the equivalent load here. It's 23.496 because I applied 10, but there is own weight, so it's more. Those are the nodal forces at the edges. This is your shear force diagram that you can move through and read. And that's your deflection shape that you can move and read. You can check out anything you want here. Of course, it's giving you here V2 and M3, which makes sense. This is the major axis and also the in-plane axis. If you want to see V3 and M2, the wind load axis, I want to call it, you see nothing because there is nothing applied. If you click on torque and axial force, there is nothing because there is nothing applied. So I think this makes sense so far, and that's basically everything I wanted to talk about today as a first introduction to how Etabs looks, feels, and thinks. With that being said, thank you very much for watching, and before I finish, I want to give a huge, whopping CEE/Etabs sized shout out to our dear channel members whose names are going to be shown on the screen. I want to thank them from the bottom of my heart as their support to the channel via their memberships is priceless to me and allows me to basically push those videos every week. If you want to consider supporting me, you can support me via the memberships by basically being a member of this channel, and I would be forever thankful. With that being said, I hope that you enjoyed the video and that it was beneficial for you. Of course, if you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.